Hey everyone. This particular lecture is a little bit out there. It's a little bit abstract. We're going to talk about composite functions here. And basically what a composite function is, we're going to be putting one function inside of another function. As we're looking at this here, this is the definition. So this is pronounced f composite g of x. And what that means is we're going to replace, g of x is going to replace the x for f in a function. So let's take these two functions here, and we're going to put g of f, that's g of f here, inside of f of x. So that x is going to get replaced with x plus h. And so you'll see as I look here, that's going to be 3 times. Now that x gets replaced with x plus h squared, then plus 5. So it's exactly this, but with the x replaced with that. You then FOIL it out, distribute and combine. Here we're going to go the other way. We're now going to take f of x and we're going to stuff it into the function g of x. So we're going the other way. F of x is this function here, and that's going to replace that x value. So you can see g of that is now the new x value in g. So here's my x, the function here, plus h. You may need to study that one, actually any of these, quite a bit. So let's move on to our next example. So here we have our function f of x and our function g of x now. And now we're going to do several composites. This first one, I'm going to evaluate g of x, specifically when x equals 2. So I'm going to go to the function g and replace the x with 2. So 2 squared is 4, minus 2 times 2, which is 4. That becomes 0. I'm now going to evaluate the function f when x equals 0 to give me 3. We're going to move to here. This is a function of the same function, and we're going to composite. So this is f composite f of negative 3. So I'm going to take the function f, replace the x with negative 3, evaluate it, and now it happens to be negative 3 also. That's not always going to happen. That just happens to be the same number in this case. I'm now going to evaluate f again at x equals negative 3, again to get negative 3. This might be a better example. So this says I want to take the function g composite g of negative 1. So I'm going to take the function g and evaluate it at negative 1. And that output ends up of a 3. That's now my new x value for the function g, so I'm going to replace both x's here with a 3. And so g composite g of negative 1 is 3. Once again, you may have to take some time to really kind of go back through this video and figure all this out. I know it gets a little complicated. So let's try this using a graph. So here I have f composite g of 0. Now I'm just going to look at the function g, which is here. When x equals 0, x equals 0, we're here. Y, or g of 0, is 1. That 1 on the y-axis here now becomes 1 on the x-axis for f. So now we're here at 1, and if I go up, I'm up 3. That's where the 3 came from. And here, we mathematically worked it out. So we're going to take f of 3. So f of 3, here's f of 3. We're up here at 2. So when I take x equals 2 for g, x equals 2, I'm up here at positive 3 again. So 3 is my solution there. f of 2. So let's just focus on f of 2. So when x equals 2, y equals 5. That means I'm going to evaluate f again when x equals 5. So when x equals 5, I'm over here at 0. Again, go through this a few times. I know it gets a little much. So here is composition, and we're going to be talking about domain as well as decomposition, which means we're going to go backwards a little bit. So here is composition, and we're going to be talking about domain as well as decomposition, which means we're going to go backwards a little bit. So here is composition, and we're going to be talking about domain as well as decomposition, which means we're going to go backwards a little bit. So the domain of this is going to be the set of all x's in the domain of G, such that G of x is the domain of f. So here's how this works. We're going to find the domain of this, specifically when, if x equals 7, do you see that y is 6? Well, no problem. When f equals 6, y equals 12. So that's kind of how the composition works. Is it kind of tags along. Picture like an assembly line in a big car company where one machine crunches some metal a certain way, it moves down the assembly line, and the next machine crunches the metal a different way. That's kind of what we're doing here. So the overall domain is going to be 1, 7, and 9. Those are the x values for G. So we're going to find the domain. And here we have f of x and g of x. And the domain of the composite function is going to be g. So x can't be negative 4. So you'll see we're skipping over negative 4 here. But when I stuff g into f, I'm here. You can see this is 2 over x, which gets replaced with this, minus 3. We then, to simplify the complex fraction here, is we're going to multiply both the numerator and denominator by x plus 4. So x plus 4 times 2 is here. X plus 4 times this is just 1. They reduce, they cancel one another. And x plus 4 times negative 3 is here. Distribute and combine, and we're here. So now we have a new restriction. We can't divide by 0. So we end up that x also, in addition to being not able to be negative 4, it's also can't be negative 11/3. So this is my domain here. And here's a graph of that with the open circles, showing that we're going negative infinity, skip negative 4, up to negative 11/3, skip negative 11/3, then off to infinity again. Next up, find the domain of the composite function. So now we have a radical. So for sure, we can't take the square root of a negative value because we're only dealing with real numbers, not complex numbers. And you can see x is going to be bigger than or equal to 1 when you set it bigger than or equal to 0, which means positive, right? And you can take the square root of 0, so it's equal to as well. And so here's a graph of that, and here it is stated. And you can see we did the composite. G of x gets put into here. And you can see when I put g of x into here, when I square it, what happens is the radical goes away. So that's how we just end up with x minus 1 without the radical, then plus 1 over here. So we just end up with x. Actually, later we'll learn these are called inverses of one another. Whenever you end up with x, that means they're inverses. Next up, we have functions f and g. And they make up function h. And here's h of x. So it looks to me like we have a function, the square root of x, and then a function x plus 5. Do you see that the x plus 5 is kind of stuffed into there? And you can see if f of x is root x, and I replace that root x with x plus 5, I'm back to h. So you can kind of see these two functions kind of embedded in there. Maybe a better example is number 4 here, where you can clearly see that the x plus 3 has been replaced. So I would say that f of x in this case is going to be x squared plus 5 over 7 minus x squared. And then g of x is going to be the x plus 3. And you can see that exactly works out here as you replace it into there. Don't worry about this example. Mrs. Ryan and I worked it out, and it's so long and complicated we removed it from the homework, so you're good.